Now that we have seen how to insert words into a list of, how to insert strings into a list of strings and search through them efficiently, we realize that most of the real-world search problems are actually not searching from a list of strings. Rather, you have to perform substring matching. So say, for example, you have a word like lexicographic. You have to match whether or not the substring graph appears in it. This is a particularly pertinent problem in the field of search. Say, for example, Google has to look through millions of web pages and figure out which web page has the string you're asking, the query string you're asking for, as a substring in the page. For this, we can naively say that let's insert all these substrings. So let's insert LEX, lexicographic, exicographic, psychographic, and so on. All of these suffixes of the string. So I'll insert all suffixes and then try not to search for the $sign. So if you have this suffix, you have graphic in your try. So from start, you have graphic in your try, and you have a $sign over here. But if you are searching and you want to match the substring graph, you can see graph and stop matching over here because you have found your the substring you're looking for. However, this can get computationally expensive because all in all there are big O of n into n plus 1 by 2 substrings, which is almost n square. So we think of a better algorithm. The idea is that we want to compress our paths so that you have many letters written in the same path. This shall be represented as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 12. So the entire string lexicographic can be compressed to one single node because all of these nodes were non-branching. So there were many nodes over here, but you don't have to represent them explicitly. Then there will be some substrings like isographic, and so you'll have isographic and just IC, which both have the same starting characters but go different ways. Here you can compress the portion of the substring IC, which is so you can use this part of the substring to compress it. So you have 4, 5 written over here, and over here you have 6, 12. Over here you have just, let's call it 13 because you have an implicit $sign over here. So 13 to 13. 6, 13 this would be because here you also have a $sign and here too. So in a word like lexicographic, you can compress all of these nodes so that the total number of leaf nodes that you would have is equal to the total number of suffixes, because note that every leaf node has the $sign at its end. So because there are only n suffixes, there will be only n leaf nodes, and since you have an internal node, only if the node branches out into 2 directions, you will have at most big O of n nodes in total. The construction of this array, the construction of this tree is complicated and done by an algorithm known as Occurrence algorithm, which we shall not be dealing with here. However, you are welcome to play with the artifacts that follow.